Good morning, everyone. So it's a pleasure to be here. So yes, so I changed a bit the title of my presentation given what I hear this week. So I will talk about this compound. This is STO. So on one hand, it's a very simple system. It's one of the simplest perovskites. At room temperature, it's cubic, and you have the titan, which is in the middle of octahedra. But still, even due to this, its structure is simple, but it displays remarkable electronic and lattice properties that I want to show you today. And essentially, my presentation will introduce you the superconducting dome of STO, and also the ground state of this system, which is an incipient modulated phase. So this is the plan of the presentation. So this is work that I'm doing at ESPCI with Cameron for many years now. And before, so you had a lot of we had a lot of discussion about the phase diagram of cuprate. But it turned out that the first superconducting dome identified in the history is electron-doped STO. This has been discovered in 1967. And as a kind of introduction, I just want to compare this dome with two other domes, so the case of cuprate here and the case of pnictite. And there is a couple of things to highlight here. The first one is that the TC span over couple of decades, 3 decades, as I will show you. And one of the most significant differences with this compound, there is two actually differences. The first one is actually it ends at 1%. And so this is extremely low compared to the case of cuprate. I mean, at this level of doping, you are still well in the antiferromagnetic phase. And the second one is that the parent compounds are extremely different. In case here you have a magnetic phase. In the case of STO, you have the so-called quantum paraelectric phase that I will introduce you to. So the ground state of STO and most of the properties of STO comes from this plot here, where you have the dielectrical constants as function of temperature. So at high temperature, this dielectrical constant that measure the level of polarizability of your system is about 300. But then when you cool down, you see that it's increasing a lot and saturate below 10K to a value which is extremely large. So it's about 20,000. So what this plot tells us is that the system wants to be ferroelectric, but it is not. Another way to plot this is to plot 1 over epsilon as a function of temperature. And from room temperature to about 30 Kelvin, it has this linear dispersion that you will expect in the mean field theory. So that means that according to mean field theory, the system should be ferroelectric, but instead the system decides to deviate and to keep these very large dielectrical constants. So this deviation has been the subject of many discussions over the years. And this phase, this low temperature phase, is the quantum paraelectric phase. The idea will be that this is quantum fluctuation that prevent the formation of the long-range order. And this feature, this extremely large dielectrical constant, has a lot of implication. First, sorry. So before to discuss the implication, I just want to show that this extremely large dielectrical constant is associated with a soft mode.
There on the plot on the previous slide on the right, the units on the vertical axis is 10 to the 3 divided by epsilon.
Yes.
And so there's supposed to be a finite intercept on the vertical axis near the origin.
Exactly. But you don't see it because the value is extremely high. Okay. So please feel free to stop me if I'm not clear or if you want some more detail. So another way to probe this extremely large dielectrical constant is to measure directly the soft mode associated with this transition, this structural transition. So you can do that using infrared measurements because this mode is polar. So this is, for example, what van der Marel studied. But you can also do that using inelastic neutron scattering measurement. So what you do in this experiment is that you take your sample, you send a beam of neutrons, and you select the incident energy of your neutrons and also the scattered neutron energy so that you can select the neutrons that are transfer an energy and a Q momentum to your system. And what is good with a neutron is that thermal neutrons has an energy of 25 millieV, but the wavelength is about 3 angstrom. That means that this is a very good probe to study the diffraction and also the phonon spectrum. So what just to be sure that we are on page with me, because I will show a lot of spectrum like that. What we do in this type of measurement, for example, is we go at gamma, we do an energy scan, and we count the number of neutrons. So this is what you have here. You have intensity versus energy for temperature ranging from 250 to 40 Kelvin. And from that, you can extract an energy position. And this is what I show here. You have the energy position of this soft ferroelectric mode, which starts to about 16 or 17 millieV, decreasing and saturate to a value of about 2 millieV, because there is the so-called lambda Sachs-Taylor relation, which tells you that the dielectrical constant, the energy of the TO mode is inversely proportional to the dielectrical constant. So the fact that you have extremely large dielectrical constant means that you have a soft mode of very low energy. So as I said, you can do that using neutron or infrared measurement, but with neutron, we have the possibility to study the Q dependence of this object. This is here, for example, a measurement in STO at room temperature, where you have the map of the intensity, where you have the Q direction here and the energy, and you can see 2 branches, this one, which is a TO mode, and then the acoustic branch here. And then when you cool down, essentially this one is going down. So this is what you see in this plot. And then it's completely dominated the low energy spectrum that you measure. Okay.
This 194, this is some sort of plasmon frequency.
This is related to the LO energy, because the lambda Sachs-Taylor relation relate epsilon 0 and epsilon infinity to the ratio of the LO mode over the TO mode. So essentially,
what is an LO mode and a TO mode?
So this is a transverse optical mode, sorry, and then you have a longitudinal optical mode. Okay.
So this is just your phonon frequency.
Yeah, this is just the phonon frequency. So this ratio is essentially a measure that is linked to the energy of the LO mode and the epsilon infinite. Okay, so here we have no electrons. I'm talking about just the insulator. Okay, so now, as I said before, the fact that you have an extremely large dielectrical constant has a lot of implication. The first one is that is a system that you can easily turn into a metal, and the basic reason is the Bohr radius is extremely high. So that means that a tiny amount of impurity in your system will turn your system into a metal. So this is here the resistivity as a function of temperature for sample from carrier density from 1015 to about 1020. Essentially, your system, which was transparent, become black, and this metal insulator transition occur at a very low density. And of course, as I already introduced, it's also become a superconductor. Here, I just want to emphasize one point because we hear a lot about non-Fermi liquid, marginal Fermi liquid. It turned out that actually this is under the impulsion of Cameron. We spent a lot of time to study in detail the electronical and thermal property of the system. And the message is that once you dope STO, once it becomes a metal, it's really a Fermi liquid. And there is at least 2 strong evidence. If you want, we can enter in detail about the meaning of all these results, but this is really the message. So here you have the resistivity as a function of T square for density from 1017 to about 1020. And you see that at low temperature on the whole range of doping, your system behaves as a T square. But even the strongest evidence that you have a Fermi liquid, we can directly measure the Fermi surface through a quantum oscillation measurement. This is here a measurement of the Nernst effect as a function of magnetic field. So as you know, when you apply magnetic field, you have Landau quantification, and that can give rise to oscillation in transport or thermodynamic measurements. It turned out that here the results are extremely nice because Nernst effect is extremely powerful quantity to study the quantum oscillation at low temperature. And this allows us to determine quite precisely the Fermi temperature energy. So in this system, we have a carrier density of 5.5 1017, and the Fermi temperature is 13 Kelvin. And it turned out that actually at this carrier concentration, the system is still a superconductor with a TC of 80 millikelvin. And this is extremely interesting because it raises the question of like how dilute a metal can stay a superconductor. So, and the case of STO is in a sense very interesting because we have a system which has a TC of 80 millikelvin, which is low, but the Fermi temperature is extremely slow. Again, just to give a bit of perspective, here you have the critical temperature as a function of the Fermi temperature. You have many systems. Cuprate are somewhere here, but STO is special because you are in this corner here. So you have a system which has a low TC, but also a low TF.
So when you say you have a Fermi liquid, you just mean that you have quantum oscillations, hence the Fermi surface, or something more detailed than that?
Yeah, it's a good question. I just say that I have a well-defined Fermi surface. Yes, this is the statement that I can say from that.
What more details were you thinking of?
Evolution in frequency, for example, or something like that.
Omega squared complement to the.
Well, I don't believe you can directly measure self energy, but that would be the omega squared would be self energy. So I don't know, maybe other signatures that I wouldn't know about.
Then you're saying it's either a Fermi gas or a Fermi liquid. Is that what you're?
No, I'm not supposing anything. I was just wondering what the statement was about.
So I believe people like von der Marel measures the energy dependence, like optical conductivity, and then you find the omega square. Maybe not at this range of doping, but at higher doping. Okay, so my point here is, okay, you have a Fermi liquid, at least from my perspective, from magnetotransport and transport measurement, but in the same time, the system has a very low TC. And so even though it's like a conventional object, I mean, it's a conventional metal, it's a conventional superconductor in the sense that the order parameter is a S wave. We are here hitting a strange limit where the Fermi temperature is much smaller than the Debye temperature. So we are in a regime where the BCF theory shouldn't work. We are in the so-called anti-adiabatic regime, where the Fermi temperature is much, much smaller than the Debye temperature. And this with other measurement trigger the question, I mean, what is the nature of the attraction in this low density superconductor?
So what is delta Debye in this system?
I will say 300, 400. 600, yeah. I mean, the LO mode, this I know it's about 100 milli EV.
I mean, then you're assuming that for superconductivity, that is the relevant mode that you coupled to.
Yes, in the usual dual approach. Of course, here there is another low energy mode, which is the TO mode. The problem is that the coupling between the electrons and this TO mode, the electron is extremely weak. So people had to propose another type of coupling, which is a quadratic coupling, where you have an electron which coupled with two TO modes. So there is a bunch of paper on this, and the sketch here. So okay, there is many things to say here, but I just want to point that the big difference with other mechanism is that that is an instantaneous pairing, and that this pairing, which has this expression here, has a characteristic length scale, which is set by the velocity of your TO mode divided by omega TO, which is about 3 nanometer. So this is an important quantity, which is the ratio of the sound velocity of your TO mode divided by omega TO. And of course, as we have this soft mode of very, very low energy, this is a very, very large object. And so I mean, I mentioned one thing that after following a couple of presentations in this paper, Volkov make an analogy between the electron pairing in STO with high energy physics. He said that this is like baryon in the cosmos. And the reason is because the interaction couple the density of electrons with the density of energy. So for me, it was not completely comfortable, but maybe here there is a kind of connection between high energy physics and condensed matter physics. So this was one axis that, as I show here. So you have the axis where you can you can add some electrons in your system. So you have this metallicity and superconductivity. But as you can imagine, the system is also extremely close to the ferroelectric phase, and it's actually possible to stabilize ferroelectricity in this system. And you will cross here a quantum critical point, which dominates the whole phase diagram. So there is several ways to stabilize the ferroelectricity. You can do that by substitute oxygen 16 by oxygen 18, or by strontium by calcium, or strontium by barium. And as I showed you already the dielectrical constant, I just want to show you now what's happening when you add some calcium. So here you have again the dielectrical constant as a function of temperature for various calcium concentration. Your pure STO is here. So here you have this quantum paraelectric regime, and you add some electrons, and at some point you see a peak, which tells you that the system goes into a ferroelectric phase. And in case of calcium, this occurs at a very small density, which is about 0.18%, which corresponds essentially at the moment where this polar regime, so essentially close to calcium, you have a polar cloud which form, and this polar cloud has a unit cell, has a length scale of 3 nanometers, and this 0.80% corresponds to the threshold concentration at which you have a percolation of this ferroelectric polar domain. So now you can ask the question, can we combine both? Can we start from ferroelectricity, put electrons inside, and what happens? So the answer is actually yes. This is actually, there's many groups that have been done that. So here you start from a ferroelectric phase, either by doping calcium and barium, and you had some nobium that do the job, and that had some electrons in your system. And the remarkable observation is that in the low doped regime of your phase diagram, you have an enhancement of the superconductivity. And really, I mean, for people who are not in this field, this is very strange physics here, because we start with two different ground states. One is a ferroelectric. Okay, so you have dipole on the macroscopic length scale, and what we do, we add electrons on that, and somehow they talk together, and then it promotes superconductivity. So here I just want to also add one thing, because we also hear a lot about pump probe experiments. There is actually another way to stabilize ferroelectricities, to apply an electrical field. This is again the same quantity. You have the dielectrical constant as a function of temperature, and you apply an electrical field. So you have the quantum paraelectric regime, and at some point you see a peak here that tells you that the system becomes ferroelectric. And as you can imagine, I mean, this system is close to many instabilities, and it's a very nice object to study under a pump probe experiment. So I'm not doing pump probe experiment myself, but I just want to illustrate the interest of this compound in this community. And so this is a result which is already that has maybe eight or 7 years old. And what you do in this measurement, that you pump your system with a mid-infrared excitation, and you measure the second harmonic generation, so which is a key tool that was introduced by Peter. And what they found is that, so here you have the second harmonic intensity. Essentially, if the signal is 0, that means that you have no ferroelectric phase. Once you have a signal, that means that you have a ferroelectric stability. And what they found is that as a function of the exposure time, the intensity is increasing. But what is very surprising in this result is that the time scale is extremely high. So you excite your system with picosgone pulse, but then over a minute, the system just changed. So it remained a bit of physics of class in a sense. And what is even more interesting is that the intensity is increasing, but also when you do the Fourier transform of this object, what you see is that you have the characteristic energy of this signal, which also increasing. So everything happened as if the TO mode harden as you go, as you expose the system to this mini infrared point. And so this is on its own a very interesting and remarkable observation, because it tells you that there is really a very slow dynamic in the system. And another interesting observation is that they map out the spatial evolution of the second harmonic signal. So here what you see is the amplitude of this second harmonic intensity in the space, so in XY space. The beam is basically the size of this graph, and they measure precisely the position, the amplitude of this. And what they found is, I mean, naively, if you expose the beam, you will expect to observe something which should be maximum at the middle, because you say, okay, I induce ferroelectricity, polarization should be maximum here. But instead, what they observe is they observe two lobes, and they suggest actually that this is a consequence of a coupling of the light with the derivative of the strength and not the strain directly. And this is due to some flexoelectric coupling, and I will come back in my second part to this flexoelectric coupling. Okay, so this was a kind of introduction on this complex phase diagram. You have superconductivity, ferroelectricity. You can combine both effects. And now I decide to talk about two subjects. One is how this L0 quantity, these quantities that set the spatial, the length scale that sets the pairing length scale in the real space evolve when you add some electron to the system. And in the second part, I will come back to this quantum paraelectric regime and show you that we identify a new ingredient to this ferroelectric fluctuation. So before that, I want to thank my colleague. Most of the sample that we use for this experiment has been grown by Tomioka. As I said, this is work that I'm doing at ESPCI with Cameron. And I will mainly talk about inelastic neutron scattering measurement that are collected at ILL, which is a European neutron source, and also at PSI. So I show you the TO mode and the dispersion at zero doping. Now the question that I'm asking is how this evolve once you add electron to the system. So what you see here is a color map of the dispersion of your TO mode. So you have energy as a function of Q for a number of electrons that just increase. So it increased by factor 10 between each panel. And what you see is that the TO mode actually hardens. And from this measurement, we can not only extract the omega TO, but also the velocity that allow us to compute the evolution of L0. So this is, again, the same data plotted in another way. So here you have intensity as a function of the energy, and you have the energy scan at gamma, and you see the mode is hardening. And now we can plot the omega TO versus n. And what you see is that it's essentially constant, that at some point it starts to harden. And in the same time, the velocity is going down. Okay. And actually, one remarkable thing in this result is that we use different type of dopants. Okay. So we use lanthanum and niobium, but there was previous measurement by Bowerley in the 80s that studied the evolution with oxygen vacancies. And it turned out that it doesn't really matter. I mean, no matter the way you dope it with lanthanum, niobium, or oxygen vacancies, the hardening is the same. And for us, it was not completely obvious at the beginning, because if you compare with the other lattice instability in STO, the antiferrodistorsive transition, there is a strong dopant variation. So here it seems to suggest that what really matters is the electrons that you add to the system. And in fact, to confirm this idea, we did in collaboration with Alaska Subdi at CPHT, we did some first principle calculation of the evolution of the omega TO versus the carrier density. So here you have the data that I just discussed. So you have the 2 millieV that's increasing and then saturate to about 15 millieV. And then on the cross here, the black point here corresponds to the calculation. So at zero doping, of course, DFT calculation give an imaginary result because the TO mode is unstable. But at some point, you see that it becomes real and actually follows the trend of what we observe. And the calculation has been done in the Gelium picture where we just add some electrons without changing the orbital of the system. So this is a good evidence that what really matters to this hardening is the number of electrons that you add to the system. And in a sense, it's obvious because again, you have dipolar fluctuation. So you have a dipole. And what you do is you add some electrons and just screen the polarization of your just screen the polarization. And the more you add electrons, the more of the screening. And just to show at very high doping, we also, we have a very good agreement between the spectrum measured by inelastic neutron scattering, which is this color map measured along 2 different directions, and the calculation of Alaska.
Maybe you're going to say it after, but maybe here is the moment to say that in this plot, it is clear that at 1020, something happens. Is this the peak of the superconducting dome or the end of the superconducting dome?
So actually it's a good question. The problem of the calculation of the DFT that is, as you know, is very sensitive to the lattice parameters that we choose. So this regime here is very sensitive to the lattice parameters that we choose. The way that we did the calculation, we say, okay, let's start from the high doping.
Yeah, but I understand the calculation, but about experimental superconducting dome.
Yeah.
1021, are you going to show it maybe afterwards?
Yes.
Sorry.
No problem.
Okay.
So this was just a kind of digression, just to tell you that what really matters here is just the electron that we add to the system. Okay. So now we are in the position where we can plot this length scale, the length scale that matters in this phonon mechanism. And so now you have here the L0 as a function of the carrier density in the linear scale. So we have these 3 nanometers, which is extremely high, and then it's decreasing to reach actually the titan-oxygen distance, which is actually the smallest length scale in your problem. Okay. So now what we can do is we can compare that with the evolution of TC. Okay, so this is a black point. So this is TC as a function of the carrier density. And for us, the first observation is the fact that the superconducting dome ends essentially when actually this length scale reaches lowest possible value. And this is interesting because it shows that the end or how died this quantum paraelectric regime is really tied to the end of the superconducting dome. Okay. So we can do one more step. Because we are also measuring the electronical property, we can measure also the evolution of the Fermi surface. As I show you, we have nice quantum oscillation. The oscillation that I show you was at low doping, but we can also measure up to really relatively high doping. And here, this is the evolution of the frequencies as the function of the carrier density. And what's happened in STO is that as you increase the carrier density, you have three subbands that you fill successfully at 2 different critical doping. So that means that we have 3 KF, and now we can compare the whole thing. We can compare this length scale, L0. So now this is in log scale. So as I say, it is constant and then decrease to reach this titan-oxygen distance. We can compare with the superconducting dome, and we can also make the products of KF over L0. And why we do that is because the density of states. The simple BCS picture, what matters is the product of this density of state times V. So density of state is just linear in KF. So essentially here, what we see is that the product of Kf times L0 has a peak, as a peak close to the superconducting dome position. So the bottom line here is to say that actually we can have a very simple description of the superconducting dome in STO, which is the product, which is a result of the competition of the increase of the density of state and the fact that as we add electron to the system, we have this length scale that's shrinking and then drive the decrease of TC at higher doping. So now maybe to come back to the point of Cameron, this transition from imaginary to real occur close to the superconducting dome, to the maximum of the superconducting dome, which again goes in direction that as we add some electrons, this quantum critical point, but we go away from this quantum critical point because we had some electron to the system. And at some point, this part is really driven by the shrinking of this length scale. Okay. So this was what I had to tell you on this story, on this electron doped STO. Essentially, we study the doping evolution of this TO mode. It's, as I show you, it's hardens, and this goes very fast. And this is driven by the electrons that we had because we simply screen the polarization of your system. And what we found is that actually the end of the superconducting dome corresponds to the point where your system goes from a quantum paraelectric to a normal dielectric. So now I will like to come back to something I'm working on at the moment, which is about this nature of the quantum paraelectric regime. So now what I will do is I will come back here at 0 and really ask the question, what is this ground states? So you already saw this picture. So you have very large electrical constants. And the usual interpretation is to say that at low temperature, there is a lot of 0-point quantum fluctuation. And this is this fluctuation that prevent the long range order. So that means that, you have to understand we are working with atoms here. So that means that the oxygen atom will move between two positions that will correspond to these two minimum, to these two levels, in this potential. And it's really an atom that will move that will move due to the quantum fluctuation, so that we have no polarization, but a lot of fluctuation. So this is a dogma for many years now. But there is another ingredient that has been discussed in the literature is the fact that at low temperature in this quantum paraelectric phase, there is elastic anomalies. And the first evidence actually was being reported by Courtins here, where he measured the acoustic mode. Okay, so this is a C44 elastic mode, but it doesn't really matter. This is the acoustic mode as a function of temperature. And you see that as you change, temperature is decreasing, but below 30 K, which corresponds to the temperature at which you have the saturation of the dielectrical constant, you have a small decrease of this hardening and of this mode. So not that the value is small. We are talking about maybe 5% here, but based on this, actually, Müller, Berlinger, and Tosati draw this picture. So they make a big jump, and they say, well, this was really an intuition. They say, oh, we suspect that the acoustic dispersion should have a Roton minimum. Okay, based on this, really, it's just they make a big step, and based on the possibilities that you have this Roton minimum, they say, oh, we are dealing here with a system where you have where you have a coherent quantum state of phonos. Okay, so this is the claim in this paper. So this has been ignored for many years, but I'm going to show you that in a sense they were correct, that there is actually some anomaly in the acoustic branch, which means that there is a coupling between this quantum fluctuation with the strain, and this is what I want to discuss with you now. I'm too late now. Should I stop? So again, I will come back to the tools that I know, that is inelastic neutron scattering. And what I do now is I do an energy scan, not at gamma, but slightly shift from gamma. So the Q vector is 0.05, 0.05. Okay. And when you do this measurement, you see two peaks. So you have one peak here and one peak here. So this one corresponds to the TO mode that gets soft. And this is the acoustic branch. Okay. And here I show the evolution of the intensity and the energy position of these two modes. And there is two things to notice. The first one is the acoustic branch at low temperature has a strong decrease of its intensity. So, and this was actually already there in the Yamada paper. And this is a signature that you have spectral wave transfer from the TA mode to the TO mode. But in addition, what you have is you have also a softening of the acoustic branch of about 0.4. And when I measure that, I mean, I was aware of the Cortins result, but I say, well, this is now a softening of 20%. Okay, so this is a huge difference. Like we went from 5% to 25%. So then I say, okay, let's continue to get closer to gamma. Okay, so now I'm doing the same experiment, but I'm going to a very small Q vector, 0.015. And again, you have your acoustic mode. This is this peak, but as you pull down, you see that the intensity is decreasing. But more importantly, the mode, energy mode, is softening. And the softening now is 50%. Okay, so maybe if you are not familiar with this technique, this is huge effect. This is like a 50% softening. It really tells you that the system wants to become incommensurate. So based on that, I did this plot where I compare the amplitude of this softening as a function of Q for the different experiments. So the neutron results are here. Okay, so as I show you, as I go to lower Q vector, the amplitude is increasing. Okay, and then we have here the Briand Hyper-Raman measurement. So that means that in between, there is actually a point where there is a strong softening of your acoustic mode. Okay, and this is correspond to this Q0 here, which is a very small Q vector. And I don't want to enter into the detail of the experiment, but this is very difficult experiment because we are working at a tiny Q vector. Here we are talking about an energy. So we are talking, which is 1 millieV. Yesterday you saw something at 1 EV. So you can imagine that at 1 millieV, you need to work very close to the bright peak, which you need to have a very high, very good energy and Q resolution. But what tell us this result is that as the TO mode gets soft, it coupled to the acoustic mode. Okay, but in a way, it's doing this in a way with a preferential Q vector. So that means that you have some quantum fluctuation that are accompanied by a strain modulation. So, and the strain modulation are extremely high. They involve 40 unit cells. Does that mean that when you, so before that, I mean, before this result, we were thinking that in each unit cell, you just have your oxygen that is moving independently. But what we are showing here is that there is actually, this involves 1,000 of unit cells. So that means that it's really huge objects. So here again, just, I mean, to kind to give a kind of overview, I just want to point also that a pump probe experiment have also recently find some evidence of this TO-TA coupling, and more specifically, they found that this TO-TA coupling is the largest at a Q vector, which is extremely small, as we found in elastic neutron measurement. So I think, I mean, it's very nice and interesting experiment here that they did. So what they did here is they pump with a near infrared, with a terahertz pump. Okay, so they send a pulse like that. They can change the sign of the pulse. And they did that on a diffraction setup so that they can measure, so they have a 2D array detector where they can measure the intensity of the bright peak very fast. So if you do that, you can do the Fourier transform in frequency and in Q. And obviously, what you would naively expect to observe is that you come with a terahertz pump. Well, you will expect to observe the TO mode. But instead, what I observe is the acoustic mode, and the largest intensity occur here at about 0.04. And what is even more remarkable in the experiment, I can change the sign of the pulse. So here it's positive, here it's negative, and can measure the Bragg intensity. So this is here the evolution of the intensity. And you see that it follows the sign of the electrical field.
So if you compare this with your neutron data, here there is no anomaly in dispersion.
Yeah, it's true. So here, it's a very good point. I'm trying to tell that to the whole community. The thing is, I don't know what they observe. I mean, in a sense, I think the interpretation is maybe more complicated. What they found is that the coupling is the largest at this Q point, but they don't really see a clear anomaly as we observed. And what is strange is that they measure at the same temperature as us at 20K. But again, what you do here is you excite, with a pump, and actually you have to understand what the pump is doing to your system. Okay, but there is differences. What I want just to emphasize is that there is clearly evidence of a TO-TA coupling. But and just to finish it.
Sorry, Benoît, didn't you explain somewhere in the beginning that as you pump for longer times, you're actually pumping the system into some
ferroelectric phase? Yeah.
Is that?
Yeah, exactly the same thing. Yeah. I think it's related to the point that when you pump your system, the system becomes ferroelectric, and it has this time evolution. I mean, remarkable or spread, you put it in there.
So you would say the difference is that this is a dynamic.
Yes, exactly. Exactly. And in my view, what they measure here, they measure a ferroelectric STO induced by the terahertz, which is classic. And okay, so then this is very different from what we are doing. But just what I found great in this result is that you see they change the sign of the pulse, okay, and they see a sign change of the strain response.
So here, what one can see is that the TA mode has amplified the intensity as 0.04.
Yeah,
is 0.04.
Yeah, exactly. It's the same because I maybe I will get here, but the answer is yes, basically. And again, also, I just want to show another result, just to tell you that there is a couple of groups that working and find more or less the same physics, even though there is differences. This is here a recent measurement of electronic microscopy transmission measurement. So what you do here is you take a very thin STO sample. I think the sample has a thickness of 15 nanometer, and you cool down it and you measure the polarization of the sample. And what they get is that they found a state which is completely inhomogeneous with characteristic length scale, which is about 20 nanometer, which is both in agreement with neutron result and this measurement. And so maybe to make a connection with the presentation of yesterday, that here we are in a situation where actually this is the physics that drive this inhomogeneity. Okay, it's something intrinsic, not extrinsic. I may come back on that. So now I want just to, again, I don't know how I'm doing about time, but right. Okay. So I want to talk about the interpretation of this physics. So there is, let's say, two ways. One which is I would say conservative and the classical, which is a classical way. So this type of coupling has been observed in ferroics. Okay. And the way that it works, so you start with your free energy, and essentially you have three contributions in your free energy. You have the one from the polarization, so which is the p square. You have the one from the strain, which is this part. And what we do is we just couple them. Okay. So you have p square, something up, and then u square. And if you do that, if you put the right coupling, so this is the so-called here flexoelectric. This is for symmetry reasons. So what we couple is the polarization with the derivative of the strain. You can actually induce an anomaly in the acoustic branch, and you can even induce an incommensurate phase transition. So this is here a plot of your TO mode, and this is your acoustic branch, and the only parameter that change is the amplitude F. So you see that as I increase F, at some point I can have incommensurate phase transition. So the claim in STO is to say that we are, and this was the second part of my title, we are incipient modulated phase. That means that incommensurability is not observed. We are just on the edge. But we clearly see an anomaly in the acoustic response. So this phase diagram is drawn in mean field theory. There is something done by Guzman-Berry and Littlewood, which draw basically the same phase diagram, except that they include Gaussian fluctuation. And they came with this picture where you have here TC as a function of this parameter F, which is this flexoelectric term, and says that you are either ferroelectric or either you have this lamellar liquid phase, which is nothing less than this melted version of this incommensurate phase transition. Okay. So this is what I will call the classical way. So maybe at the end, the quantum paraelectric regime is nothing less than two-mode coupling, and that prevents the formation of the ferroelectricity. But there is another way, which is to say, oh, maybe if you really believe that there is quantum fluctuation, you may say the objects that we found here are actually instantaneous. So I'm using this word, I'm not completely sure to know what it means, but the idea is that you have something which helps you to tunnel. Okay. And so now I think we are, in function of what you like or what type of physics you are more familiar with, you can choose. But I think at the moment, the question is really to know, are we still dealing with quantum fluctuation? So that means that does this classical way explain everything? Or do we still need to invoke quantum fluctuation for the ground state of STO? So yeah, so 10 minutes. I can, so this was previous work. Maybe I will stop here in a sense, because after we did much more studies, or maybe I can try to summarize it in few minutes, but motivated by essentially this work, we say, okay, now let's take our STO, push it in the ferroelectric phase and see what's happened to this TO-TA coupling. And as you may remember, that there is several ways to tune STO into a ferroelectric state. You can dope with calcium, you can dope with barium, or apply an electrical field. Okay. So I can show you just, we maybe go directly here to the result, that this is here our study under calcium concentration. And so the system becomes ferroelectric. And what we actually find, in kind of contradiction with the phase diagram drawn by Littlewood and Guzman-Berry, is that as the system becomes ferroelectric, the anomaly in the acoustic branch is actually increasing. So that means that somehow ferroelectricity and this incipient modulated phase cooperate rather than competing. And maybe I will maybe end here to answer to the question of Cameron. Now, we not only found that the amplitude is increasing, but the position at which this minimum is also changing. So this is Q mean, the position where we have the minimum in our measurement that is increasing with calcium concentration. And this is a result of the pump probe experiment that I show you. And if you keep in mind the fact that when you put terahertz, you turn the system into ferroelectricity, there is a kind of consistency between the calcium result and this result. So I will stop here. I just want to emphasize that we are here. There is a kind of, the ground state of STO is really like a very weird object. This is not just about quantum fluctuation or titan oxygen fluctuation. It's really an hybridized state. And this is driven by the combination of the soft TO mode and the existence of this flexoelectric coupling, which give this very this fluctuating phase, which is in a sense can be reminiscent of scribe fluctuation, if you want, in the case of cuprate, for example. But here it's purely driven by the force. So with that, I will stop and thank you for your attention.
Questions? Yes. So just looking at this, your Q mean is becoming larger as you go with calcium. Yeah. So the length scale becomes small.
Yeah.
So your interpretation, this length scale is intrinsic. Is that correct?
Yes.
So because I
Yeah.
follow it. So the whole idea is that in pure strontium titanate with no impurity, somehow atoms connect to each other over 40 length scales. But this length scale becomes smaller when you make the. Is there any?
No, I mean the problem is so of course we feed the data with this classical parameter, this Ginzburg-Landau parameter, and we just have a parameter f, and we just put it in the fit. But for the moment, we don't have an understanding of the macroscopic or what are the parameter or that control this flexoelectric term.
Okay, just because you never defined flexoelectricity.
Sorry.
It is a strain dependence.
Yeah, so flexoelectricity, I'm sorry if I went too fast. It's is actually the term that couple polarization with the derivative of the strain, or the inverse, like strain with the derivative of polarization.
But this derivative of this strain is not because of any impurity.
No. This is really
hormones.
Yeah, sure.
So it means that you all have some kind of nonlinear.
Yes. It's not. I mean, it's linear, but it's not related to either polarization or strain. It's just related to the derivative of these objects.
Maybe to connect to this question. So when you increase the doping, do you see a broadening of the line shapes that comes with this? Shift to higher Q? Because that may actually be a way to understand this. I mean, if you add impurities, then you will essentially pin these fluctuations and they become more.
It's a good question. I don't have a definitive answer because even in pure STO, so STO is a very weird object. Like when you measure, for example, if you measure like the acoustic branch, so you cool down your sample, you measure like you make an energy scan at Q vector to see the acoustic mode, you warm and cool down, you see that the broadening change. So and I have not that explanation. So this is why
may be domain physics, no?
I don't know.
But I mean, in general, do you see broadening?
No, not because again, keep in mind that the calcium concentration that we put here is very little. It's just like 1%.
No, but it gives an appreciable shift, right?
Yeah, but it gives a shift exactly. So, but even for example, on the lattice parameter, you don't see it.
So would you be able to do this locally with a local probe that you can look at the lattice parameter and see if the doping itself affects?
Yeah, I mean, so what is so there is certainly an effect of. You're right. I mean, calcium. I don't know how much calcium are distributed in the sample. I suppose it's homogeneous. So yeah, we should measure it, but I don't have the competence. I mean, we should use microscopy, electronic microscopy measurement even at room temperature.
So I have a comment about this question. I think calcium is distributed homogeneously from this experimental evidence. If you look at the anomaly of the specific heat at AFD transition, so there is a structural transition at 105 K. There is no broadening of that transition. So the TC shifts, but 1% of calcium doesn't change the broadening. So most probably it's, well, as far as we can say, there is no inhomogeneity in calcium.
And there is no big effect, but it does not mean that it does not play any role.
But you see, you mentioned instant. Can you tell us what is an instant?
Well, I mean, okay, just because, so I wrote that in the paper like 3 years ago. So 3 years ago, it was clear in my mind, but now it's less clear. But I say, okay, maybe Corentin, you can explain us now, or because I thought it was written in one of the Cambridge group also, on the Cambridge group.
I don't fully understand what the Cambridge group is fully thinking about this always, because in particular the flexoelectric coupling and the way they process it theoretically, I'm not always quite clear on this. I have a semi-answer on this. The way I understand this is similar to what some people have done with SSCHA. Okay, if you know that, it's where basically instead of just considering phonons like classically in the sense that you have balls that are moving around and that are in potentials, you consider the whole wave function of the nuclei, and then your nuclei can do funny stuff like this. that is what SSCHA does, and that's what I understand. Where basically, yeah, you can have some tunneling. I don't know if really saying that you have particles like quasi-particles which are different helps too much in understanding it. For me, it's more like if you can calculate phonons using the full wave function behavior of your nuclei, you go basically beyond Born-Oppenheimer. Then you get results which are a bit more close to it, right? That's what I understand.
But I think the claim was more like so. I mean, maybe you're referring to Spalding paper. I mean, I think
no. There is the person who did this is in Bilbao, I think. I forgot his name.
But the point here is to say that we have. I mean, due to this, the question is we have this fluctuation, and then they couple to strain, and the question is, does it help to stabilize this quantum fluctuating state? And the way that, I mean, the picture that I had is just that essentially this coupling allows, it's like if you have like a train, which, will help you to pass the barrier. So this is the way that I saw this object, the strain deformation that allow you to couple. What is not clear for me is how, because now we are talking about thousands of atoms. So this is big objects. So yeah, this is for me unclear if it has any sense, and this is why maybe at the end the classical interpretation is the simplest one, but maybe we are missing also some physics here.
Thank you so much for very exciting results. So I have two questions. So the first part on superconductivity. So if I understand correctly, the interaction that is mediated by this ferroelectric soft mode has a characteristic exponential damping in real space. If I Fourier transform this, I will obtain something like a Yukawa potential, right? So do I understand correctly that the range of the interaction increases in real space with decreasing doping?
So L0 is decreasing. So yes, it's increasing. Yeah.
So in some sense, if we assume that this interaction is somehow connected to superconductivity, as we increase the doping, the model would become more BCS-like, and as we go lower in dopings, essentially it becomes more akin to an interaction like Coulomb interaction.
Yes, exactly. Yeah. I mean, at low doping, the picture is you start with these super fluid fermion models by Gorkov, where you have EF, and this is EF times exponential minus 1 lambda. And then when we go to higher doping, we recover the usual PCS picture. Yeah.
I see. But
the thing is, the connection between the two models is not clear. I mean, I think, for example, Fagelman is really just, I mean, all the paper just focus on the low density. The extension is more difficult, and the connection, I mean, it's not so obvious from technical point of view, but this will be the naive way to understand the crossing.
But just one thing, there is no BCS superconductivity, because as soon as you arrive to this, when your characteristic length changes, you lose superconductivity. And one of the things about perovskites is that there is no other superconducting electron phonon mediated perovskite with this structure, in the sense that if it was BCS, density of states is large, so STO is unique among perovskites to have this dilute superconductivity. So KTO maybe is an interesting case, because I interrupted you.
No, sure. I see. And right. So and also you mentioned oxygen reduction as another possible way of doping the system.
Yes.
If I understood correctly from you had discussions with skilled experimentalists as you, the superconducting dome is a bit different there.
Yeah, sure.
So do you think these two ways of doping are leading to different types of microscopic origins of superconductivity?
Well, it's a good question, because the low densities only observed in oxygen-reduced sample, and effectively. So, I mean, at the moment, what we know, actually, this was in this. The thing is, what we also understood is that the Fermi surface are also different when you dope with oxygen and lanthanum. Okay. So at the moment, I mean, it's so I would say it's more like in the Fermi surface sector that we clearly identify some difference. So now for the mechanism, it's hard to say. And again, yeah. So my answer is more like Fermi surfaces are different.
Is the Fermi surface when you have oxygen 18 doping the same as in undoped? That's what you would expect, right?
Yeah, it's a good question. I don't remember. We should look the paper of Willem that study. It's a good question. I don't know.
Any other questions? If not, let's thank Benoît again.